All right, folks, so in this video, we're gonna add the sensor model, but first thing that we need to do is, unfortunately, we need to get rid of this fixed step integrator, or sorry, adaptive time step integrator, and we need to move to a fixed step integrator. And so I'm just gonna code my own RK4. And so this T-span needs to get replaced by something with a time step, okay? And so I'm gonna make the time step 0.1 for now. I'll change it later. I just wanna make sure this works. And the T-span is gonna be changed to T-final, and that's gonna be period times number of orbits. And then my T-out vector is gonna be 0. It's gonna increment by the time step, and then it's gonna go to T-final, and then that's it. Now we're going to make a loop. Instead of here, we're going to say for IDX is 1 to length of T out. And if you recall, down here, I did all this BX, BY, BZ stuff. I actually get to move this up into here because now basically these loops are the same. So I can actually delete this one and end this here. And then let's see, loop through time to integrate. And so now I need to create my state out vector. So state out is going to be what? It's going to be zeros, length of T out, comma, the length of, is it state out 0? State initial. Oh, and that same thing happened again. If I just, length of state initial. All right, my Java thread just should have break. All right, I'm gonna pause this. I'll come back. All right, and we're back. Okay, so state out is the number of rows is the same as T out, and the number of columns is the same as state initial. Okay, this does get a little bit tricky because what we need to do is we need to, every time we come through this loop here, we need to save the current state. And so I'm actually going to change this from state initial to just state, and then change this from state initial to state, because state is going to constantly be changing through this loop when we do an RK4. I have other videos on RK4, so I'm kind of just going to do this really quickly. So we need to save the current state. So we're going to say state out of IDX comma all is equal to state, but we need to transpose it because state is a column vector, and we need to transpose it to a row vector in order to put it in there. Then we make our 4 function calls for the RK4, and T out IDX is good, but we need to do state now because that's a column vector, and this is not going to be d state dt, it's going to be K1. And then K2 is going to be the dynamics of T out IDX plus time step over 2. This is the RK4 algorithm. And it's going to be state plus K1 over K1 times time step over 2. And then I'm going to copy this 4 times because then we do K3, K4. And then this is time step over 2. And then this is time step. And then this is K2, K3. And this is time step not over 2. And then what different books call phi, which is not to be confused with the Euler angles, is 1/6 times K1 plus 2 times K2 plus 2 times K3 plus K4. And then, by the way, I think this is in my spaceflight mechanics book. I think if I go down to, Runga 4, bam, there it is. There's the time step plus T over 2, or sorry, T plus time step over 2. There's the 4 function calls. Okay, I called it K. All right, let me stay consistent. Instead of calling it phi, I'm just going to call it K. So that's 1/6 K1 plus 2 K2 plus 3 K3 plus 4 plus K4. And then the next state is the current state plus K times delta T. So then basically I'm going to say state equals state plus K times time step. Okay, and then this is where I save the magnetic field and populate it in that vector. And so this should all just do exactly what I want. So what I want to do, a couple things just to make this look nicer, is I want to have a print next. So I want to have a next equals, I'm going to say every 1 second. And then I'm going to say if, let's see, T out of IDX is greater than next, then print or display time equals, and I'm going to make this a string, so time equals num to string oftout idx, and then I'm going to say next equals, ooh, I need to say last print, I need to say last print equals last print plus next, and then last print is going to be initialized at 0, and then say end. Okay, so now let's see. So this is going to go all the way to whatever the period of the orbit is. What's the period of the orbit? Is it? I think it's 5400. So this has to get all the way to 5400, and then it should plot. And so there's our magnetic field, which looks good. There is our orbit. There is a significant amount of aliasing here because our time step is too large. And then, but our orbit is good. So that's an interesting thing there that we have to play with, and I'm not sure exactly how I want to deal with that. But basically, the time step of the translational dynamics is way different than the time step of the rotational dynamics. And again, I'm not sure exactly how I want to do that. Because the orbit is, 5790, I'm going to have this print every 100 seconds. And so now it'll only print every 100 seconds, which is fine. Okay, so one thing that we want to do to save some time is we want to slow down the magnetic field model. So what we want to do is we want to do the exact same thing. Oops, let's see. The same thing we did with last print and next. We want to do last mag update and next mag update. Okay, and then I want to define those somewhere. So where do I define the magnetic field stuff? Here. So I'm going to say last mag update. I'm going to say next mag update is, I think every 10 seconds is fine, to be honest. So I'm going to say next mag update is 10 seconds. Last mag update, I'm going to say -10. So that, or minus next mag update. That way the first time it runs through, it'll update and then it'll initialize at 0. No, I don't want to do that. So I'm just gonna make it 0. So it'll update right away, and then it'll go from there. So, ooh, I need to make this like -1e negative like 100. Just some like really, really small negative number so that it updates on the first go. Because if not, T out, the first T out is going to be 0. So 0 is not greater than, oh, unless I make it greater than or equal to. Yeah, let's do that. So I'll make it 0, and I'll do on here, when I update the magnetic field, because BX, BY, and BZ are globals, they're going to preserve from time step to time step. So what I can do here is I can say, call magnetic field only if the T is greater than or equal to next mag update. And up here, I want to put in next mag update and last mag print, or last mag update. I think those are the variables. And so here, then I can say next mag update equals, no. I want to do last mag update. The last time we updated, and then you say last mag update. So basically the next time you update is going to be the current value plus the step value mag update. Okay? And then shoot, I can just block over this and then say end. So that's only going to update when I want. Okay? So let's throw down a tick and a talk. So I'm going to do tick, and I'm going to throw down a talk. And so that's going to tell me how long the code runs, or how long the code runs. So my time step right now is 10, and I'm calling the magnetic field model every 10 seconds. So let's see how long this takes. Oh, that was fast. Yeah, so 1.3 seconds, right? Ooh, that was interesting. Did you see the magnetic field? I don't think it updated every 10 seconds. Yeah, it like updated once and then like never again. That's why it ran so fast, because it just like updated once. Let's see what's going on. last mag, if t is greater than or equal to last mag update, and then next mag update, last mag update is 0, next mag update is 10. Am I sending time? I'm sending time. Should we throw a debug point in here? Let's throw a debug point in here and make sure this is working right. Okay, so last mag update is 0, so this is gonna be 0, 0, and empty. Uh-oh, next mag update. Why, did I spell it wrong? Next mag update. I did. Oh, update. Okay, run it again. Oh, I don't need this debug point. Quit, back to main. Okay, so now you can see it's taking a lot longer to run. So that was 3.8 seconds. So the more times we call this model, the longer it's gonna take to run this simulation. So let's see if we can find the minimum number of times we need to run this magnetic field model. So let's try running the magnetic field model every 100 seconds and let's see. So that ran a lot faster. Let's see, ooh, to be honest with you, I'm okay with that. It's updating every 100 seconds and it looks like an old 8-bit game, but I'm totally okay with it because my simulation time is way better. All right, so now let's drop down my time step to 1 second, okay? And run that. How are we doing on time? 11 minutes, just making the code ready for the sensor model. Not too bad. Okay, so now we're at 4 seconds sim time. Magnetic field model still looks terrible. Norm still looks terrible. Angles still look terrible at 1 degree per second. So we're still not fast enough. If it's 1 radian per second, I think in terms of aliasing, we need to have our time step 2 times less than that. So I think we need a time step of at least 0.5, but I'm gonna try 0.1. Ooh, that's so freaking slow though. So here's another thing that we can do. We can just rotate the satellite slower. So I'm gonna hit Control C and kill it. I'm gonna keep the time step at 1 because I want the system to run faster. And then if I'm using my Nyquist frequency, I can't spin the system faster than half of that. So I'm gonna try to spin the satellite just at 0.1 and see if I capture the rotation correctly. Let's see what happens. Because I'm a tenth lower now. Okay, that looks pretty good. So I'm gonna stick with that. So I'm gonna keep everything at 0.1 or lower. So I'm gonna do 0.08, negative 0.02, and then negative, and then 0.03, and let this thing just kind of tumble on all axes, and let's see what happens. Okay, so there's our orbit still looking good, our magnetic field looking terrible, but that's fine. And then here is our, our rotations. Our satellite is spinning, right? So it's tumbling about all axes. It's going from -3 to 3 because it's overlapping on pi. And then here's our angular velocity. That looks odd. Is that PQR? It's perfect. Why is it just perfectly rotating about that axis? That seems kind of odd. Let me pause it real quick and make sure that this is working right. Okay, the reason why that third axis doesn't rotate is because the inertia matrix is perfectly diagonal. There's no cross products of inertia. And then then PQR, even though that's a 3x1, if you do I times PQR, all that did was scale that vector. It didn't actually rotate it, so it just scaled the vector. And so if you do PQR cross that vector, if you do cross PQR I times PQR, you get 0 in the third axis because you've got 2 vectors in the plane. And I feel like that makes sense, but I'm not entirely convinced. PQR is this, I times PQR is this, and so yeah, are these things collinear? Do I have a matrix called skew? A function called skew? No. Yeah, those vectors almost look like they're in the same direction, don't they? Oh, I see what happened. They got scaled disproportionately. So the x and y axes so if you have 2 vectors, right? So this is PQR and this is I times PQR. So it got scaled in the XY plane disproportionately, and so there's a small angle between them. So, but the z-axis was the same, or the z-axis is a little different, but they got scaled disproportionally in the x and y axis. So when you cross product them, they immediately go in the plane. So if I wanted that third axis to topple differently, I would need cross products of inertia. So I'm gonna say this is fine. All right, so yeah, we're coming up on 15 minutes. I still haven't even coded in the sensor model. So I have the system rotating, I have the satellite dynamics, and now it's time to run the sensor model. So what I want to do is I want to say, let's see, I have here if t. So I'm going to do the same thing for the sensor model. I'm going to see if t is greater than or equal to last sensor update, then last sensor update is equal to last sensor update plus next sensor update. So this will give me my discrete nature just like I did before. And what I'm going to do is I'm going to say B field measured is equal to, well, I'm going to say B field measured and PQR measured is equal to a function called sensor of the B field in the body frame and then PQR. And then I think I have PQR defined up here. This is B in the inertial frame. I need B in the body frame, which means I need TIB of phi theta psi. No, because I need to do quaternions. So I need TIB quaternion of Q0123, but I need to do the transpose because I have the inertial frame on this side and then I have the body frame on that side. And then I don't think I need, do I need BB to be a global? I don't think I do because I'm not going to use it anywhere else. Okay, so let's end this. Let's see, there's a lot, oh my gosh, there's a lot to do right now. So first I need this TIB quat, so let's go do that first. So I think I have an R quat somewhere. Where's the R quat? There it is. There's R quat. And then I'm going to throw this in here, and I'm going to call this TIB quat. And then open that up, TIB quat, and then TIB quat. Let's see. Yeah, see, compute R such that V inertial is equal to R V body. And so I need to transpose this. Mark Costello is my advisor. Let me delete him from this. So this is going to be TIB, and so this is why I need to transpose it because I want body on the left and inertial on the right. I want Q0123 to be one function all at once, and so this is where I extract it. Q0123. Q0123, Q0123, Q0123. Boom is a program that my advisor wrote, and I kind of stole this from him. I guess I should probably remove this copyright since I changed it to MATLAB. Code is always borrowed. I'm not entirely sure. You know what I'm going to do? I'm going to leave my copyright and say that matrix originally adopted from Boom 2010, Mark Costello. Okay, give him some credibility there. Okay, so I think this is good. I think this is going to give me my R matrix, and we'll be good to go. So that will take a quaternion and rotate me to the body field. So now I need this last sensor update and next sensor update. I need those to be globals. So I need last sensor update and next sensor update. And then over here in main, I need to define some sensor parameters. And I want to say I should make a function called sensor params because I think there's going to be a lot in here. Well, I'm not sure. Either I make them, yeah, let's just do sensor params because I'm going to use them a lot. So sensor params, and so I'm going to make a new function called sensor params. Oops, I want to do .n. Say yes. Okay, and I want to do, let's see, last sensor update is, that needs to be initialized in here. Good thing I caught that. Last sensor update needs to be 0, okay? And then over here I can do next sensor. See, that needs to be over here too. Next sensor update. How often do we want to poll a sensor? Once a second, 1 hertz, that sounds fine. So next sensor update, I don't need that, but I do need bias and noise. So I'm going to say mag field bias, and I want to do a random number generator. So if I do rand, that is going to give me a uniform number from 0 to 1. So I'm going to say, how much nano? So it's typically on the order of like, what's the nanotesla of the, is it like 30,000? It's like 30,000 microtesla, I think. Where are you at? Here you are. All right, here you go. So it's like 4 times 10 to the 4 nanotesla. So I'm going to say my scale, my mag scale bias is 4E4, and that's nanotesla. And so if I do 4E4 and then E minus 9, that's basically the same as E minus 5. And so that's a lot of bias. So I'm going to say the bias is like E3. And so then what I'm going to do is I'm going to take the mag scale bias times 2 minus that random number. Okay, so let me see if that makes sense. So if it's 2 minus 0, no, that's not right then. See, I want minus 1 to 1, and rand goes from 0 to 1, so that means I need to multiply rand by 2, so that way it goes from 0 to 2, and then subtract 1 from the whole thing. Yeah, I think that'll work. Okay, so there's my mag field bias, and then I want mag field noise, and I'm going to make this smaller than this, so 1E minus 4. Wait, if I did minus 5, didn't I make it bigger? Minus 3 made it bigger. So let's make it minus 7. Mag scale bias is minus 7, and then let's make this minus 9. So that's like, it's going to vary, the noise, well, that's not very big. That's fine. So this isn't nanotesla, this is Tesla. Oh, I see. So 4E minus 9, I'm having a hard time getting a right scale for this. I'm just going to leave it. I'm going to leave it as 4E minus 9 and 1E minus 7 for the noise. And then I'll deal with it later. All right, so the mag scale noise is the mag scale bias, or sorry, mag field noise, which is the mag scale noise there. And then I'm basically going to copy this again and then change everything from mag to angle, because this is going to be the angular velocity sensor, and this is going to be radians per second. So I'm going to say the noise is on the order of 0.001, that's the bias, and then the noise is going to be on the order of 0.0005 radians per second. And then ang. I might make another, this is getting long, I might make another video, because I spent so much time on the sensor dynamics, I might put the filter in another video. Okay, so I think this is good. So this has all of our bias and noise with random number generators. And so in the, I think I can get rid of TIB quat to Euler, Euler to quat, and then in the satellite class, when I run this, that's right, I need to make a sensor routine. And the sensor routine is going to have this in here, copy, paste, function, conjunction function, and we are going to run the sensor params, okay? So get our sensor params, and then we're going to pollute the data. So PQR is going to be, oh, but do I want the bias and noise to be the same for all of them? Can I just run this 3 times? That's sloppy, but I'm gonna do it. So BB of, what is BB? Is it a 3 by 1? Yeah, it's a 3 by 1. So we're gonna say BB of IDX is BB of IDX plus the bias, which is mag field bias plus the noise, mag field noise. And then PQR of IDX is, ooh, I see. I guess I'm going to take the input and just output the output. Or take the input and just send it as the output. But it doesn't matter because these outputs are going to get renamed. When you come back here, they'll get renamed, so don't fret. Okay, and then we're going to say PQR IDX plus ang field bias plus ang field noise. All right, and I think that will be it. There's the sensor block. I don't need this semicolon. And then I kind of want to make these B field measured and this PQR measured. I want to make those globals. So I'm going to say B field measured and PQ, is it, what is it? Is it PQ? I should put this on another line. Global. B field measured. Is it B field measured? Let me just copy it. Copy. Paste. So PQR measured and B field measured. And the reason why I want to do that is because in main, I basically want to copy these 3 times and say BX. Ooh, these are body frame. Now we have issues, right? Because let's not plot the inertial. Let's do, let's plot the body frame. That way we're comparing apples to apples. And actually, I don't even really need this anymore because I can just make BB a global. So let's just make BB a global. Okay, go back to main, make BB a global. And then that means I also need to make what? I think I need to make these globals over here, don't I? I already did that. Oh, but I didn't do the last sensor update. Last sensor update, next sensor update. So let's get last sensor update. And then next sensor update, and then PQR measured. Okay, there we go. All right, so then down here, we're going to change this from BXI to BXB, 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 and then BXB, BXB. And then down here, when we save the variable, we're going to do B, B, B. And this is going to be BB of 1, BB of 2, BB of 3. And then we can do what I was trying to do before, which was copy this twice and do BXB measured. So I'll call it BXBYM, BXBY, BXBBN. So those are the measured signals. And then basically copy these twice and then call this BB, what is it? What was the variable name? B field measured. So we'll do B field measured. B field measured. I feel like I'm losing my audience. I'm losing myself. This is getting crazy. I'm gonna upload this just so you can see it. If you just like fast forward this, or like I lost you 10 minutes ago, like I don't even feel bad, because this is getting crazy. But at least you'll have the code. So I also want to save the polluted PQR signal, and so I need PQR. Oh, this is M. This is M. This is M. PQRM IDX, and this is what is it? It's not ang field measured. It's PQR measured of 1, and then copy this twice. Wait, why do I have IDX? Oh, okay, that's fine. I'm gonna do all. And just save the whole thing, but transposed. And then I'm going to make a PQRM. PQRM equals zeros length of T out, comma 3. And then I want to plot. So this changes to B, to B, to B. And then I don't want the system to rotate this time, so I can actually like debug this, because I want the magnetic field to be a little bit, I want the magnetic field to be constant in the body frame, and if it's rotating, it's just going to be going crazy. This needs to be BBB, BB out, BYB, BYOB. Okay, and then BXB out. Wait. Oh, okay, I already changed that. Okay, so then we have the Euler angles on. Okay, so then I'm going to do a hold on. I'm going to plot T out PQRM. I'm going to plot this in red dashes. I'll just plot it in dashes in general. Okay, so then the solid lines will be the actual, and then the dashed will be the measured. And then that means I can do the same thing here and change these all to BXBM dash dash B. Oop, wait, what did I do? I did that wrong. Down here, BXBM dash dash, get rid of these because I already have them. BXBM dash 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 BBM. And then here come all the errors that we need to fix. Oh my gosh. Call NASA and tell them that we just ran code without errors in it. Holy mackerel. Okay, so here, I thought I did a hold on these. What the heck? That looks good. That looks like some polluted data. I like it. Yeah, there's my solid signals in there. What the heck is going on with this one? The mag field, do I just have, like, do I not have a hold on or something? Let's see, I plotted them here. Here's the mag field, yeah. BXBM, BYBM. Do I save them? BXBM, B field measured. Okay, and then I have B field measured is here. Did I save this? I didn't save it. B field measured is here. B field measured is here. Here's where I send the body frame. And then if I go to the sensor dynamics, here's BB, BB, mag field, and mag field noise. And then where are the sensor params? Oh, is it possible that they're just too tiny? That's possible. Let's run this again. What was the scale? And we got to call this video a day. 33 minutes. This is way too long. No one's gonna want to watch this. Okay, so let's see. So this is in nanotesla. Did I multiply? I'm gonna move this out of the way so I don't get it out. Are you sure it's in nanotesla? Oh, wait a second. This IGRF model, how does this work? Does it output? What's the output? Inputs, outputs in nanotesla. And do I convert it? I do not. Ooh, shame on me. Convert to Tesla. So then I need to go back to main and freaking change this to Tesla. Let's try that again. What? Oh, if you click on the folder, you change your directory? I don't like that. What time is it? Almost 10. I gotta finish this code. All right, can we at least verify that we are plotting? That is like no noise whatsoever. That's hilarious. It's there. Okay, so I'm gonna call this video a day. I can change the noise however I want, but the sensor dynamics is coded, and I will do another video for filtering. All right, see you in the next video.